All right, welcome back. We are Game 2005 in the fall 2020 semester at George Brown. It's Game Physics, and it's Week 11, Part 1 of our broadcast. We're talking today about collision response. And here's we are. We're actually here at Week 11, not at Week 12, not yet. On Week 11, we're still into 2D stuff. Just as a reminder, your assignment number 3 is slated to be submitted next week. Okay, that's when it's due, assignment 3. Also next week, look for a couple of changes. One, some kind of 3D framework is the plan, right? Where you'll be working with assignment 4, which is going to be done in 3D. All right, that's coming up. So that's next week coming up. Assignment 3, again, due next week by the end of the week. Okay? Okay, I'm going to go back into this now. Any questions around the schedule before we begin? So again, we're running into the last part of semester. We have 4 short weeks left, including this week is 5. The final test, again, just as a reminder, there will be no final lecture in the final test. We'll be using that time for any kind of Q&A, as I will be giving you a practical test to complete for the end. Okay, something that's based on collision detection and response. Okay, something that's straightforward for you guys. All right, so that is what's happening in the final test. Again, week 14, there's a special topics plan. Maybe we'll do particle systems. We'll see how it goes. I may also use this special topics week as a review week, where there'll be a chance for us to look at your assignment 4. Okay, so that's kind of another option for us. Maybe like a presentation or something like that. Other than that, excuse me, we're really into 2D collision response as well. Raquel's asking, is it going to be just on that day, or will it be like the midterm? Just like the midterm. You'll have the entire week. Raquel, I'm not going to time limit you. Again, I don't want to cause you guys unreasonable stress. There's no need for that. I'll give it to you at the beginning of the week. It'll be something that you can complete within a couple of hours, and then you'll have a chance to do it for the end of the week. It's supposed to be individual, but again, you can talk to people, you can look online, you can do all the things that you need to do to make sure that you are successful. Okay? The only thing I'd ask you not to do is copy somebody else's code, and if you do, that would be bad. Okay. So let's get moving on this. So today we're talking about collision response. There's 2 parts. There's part 1, where there's a momentum and impulse, and part 2 is way down in here. Again, we may have to move off part 2 to another day because there's 119 slides that I've got in here. Lots of stuff to cover, and we've got 2 short hours to do everything. That's like a slide a minute. And there's no way I'm going to be able to cover a slide a minute. Chances are. I may have to skip some slides, but that's only because it might make sense to do so. So really what we've been talking about last week was conservation of motion. We talked about the conservation of motion idea. And here what we want to talk about also is the conservation of linear momentum. Remember, can someone tell me the difference between momentum and inertia? We talked about these two concepts in the past, and I'd like to know from you guys, does anyone remember from last week the difference between momentum and inertia? Anybody? All right, well, inertia is almost like, we got Vincent, is inertia and mass are interrelated? Yes, they are, right? But what is inertia? If I was going to say an object has inertia and it's interrelated with mass, what does it mean? It means, okay, Sam says an object, Sam, I haven't talked to you for so long. I miss you, Sam. An object in motion tends to stay in motion. Momentum. An object at rest tends to remain at rest. Inertia. This is from Newton's which law? Newton's first law, right? And so what it is if an object is at rest, I want to try and move it. How difficult it is for move an object is its inertia, right? Or its mass. The more mass it has more. We can say it has more inertia. It's more difficult for me to get that object moving. At the same time, on the other side, if I have a lot of momentum, mass times velocity will give me a momentum value. If I have a lot of momentum, it's how difficult it is for me to stop that object from moving. The more momentum it has, the more impact the object is going to have when it hits, if it does hit something, and there's going to be more energy involved, energy transfer, for me to try and stop that object from moving. Okay, so that's momentum. Okay. So again, we talked about isolated systems versus non-isolated systems. So here what we're talking about, momentum of the system is conserved. What ends up happening is we keep it, and it also tells us that the total momentum of an isolated system equals its initial momentum. So whatever, remember, in the conservation of energy, if you will, or motion, energy is neither created nor destroyed. It's maintained. We maintain the system, right? We move the energy around. We don't create it or destroy it. And so we have some math related to this, where we have the total momentum. Momentum is represented by P, right? As an example, is equal to the, if we add P1 and P2, we get the total momentum as an example. Or we can also say that P initial is equal to P final, right? Okay. So again, when we think about momentum, the conservation of momentum can be applied to systems with any number of particles, and the momentum version of the isolated system model states that when two or more particles in an isolated system interact, the total momentum of the system remains constant, which means if I'm moving the entire system around and the things are inside that system, we don't care. The momentum of the entire system stays the same. Okay? When we look at forces and the conservation of momentum, right, we don't really care about specifically whether it's conservative or not conservative as a force. We don't really specify that. We don't know if a force is constant or not. The only requirement is that forces must be internal to the system. And this gives us a hint about the power of this new model, because what ends up happening is, as an example, the momentum is conserved inside the system. So here's an example. A 60 kilogram archer is standing on the frictionless surface, ice, classic example by the way, and fires a 0.03 kilogram arrow horizontally at 85 meters per second. Okay, that's the velocity. With what velocity does the archer move across the ice after firing that arrow? Okay, can we use motion? No, we have no information about velocities other than the arrow, all right? Can we use Newton's second law? Force is equal to mass times acceleration. We have no information about force or acceleration, so we can't use Newton's second law. How about energy? We don't really understand anything about energy. That we don't have any potential energy or kinetic energy. Remember, from an energy to work, he's not moving, this guy, right? All he's doing is standing there with an arrow in his hand, and no movement, no kinetic energy. Remember, kinetic energy is equal to mass times velocity. Here, he's not moving, so we have no idea what's happening. However, momentum does play a role. So we'll conceptualize. The arrow is fired one way, and the archer recoils in the opposite direction. Newton's third law. For every action, there is an equal and opposite reaction, right? Which is where this idea of response comes into play. So again, from momentum, let the system be the archer with the bow. That's particle 1. And the arrow is particle 2. Two different things here. It is not an isolated system in the y direction because the gravitational force and the normal force act on it. We're talking about the arrow. There are no external forces in the x direction, so it is an isolated system in terms of momentum in one direction, in the x direction only. So we apply the isolated system momentum model in terms of momentum components in the x direction only. Okay, remember, y direction is going to fall down, but the x direction we can look at and say we can apply momentum here, right? So because momentum is conserved, right, we know that the amount of force that he's putting into it, so again, the change in momentum, P, it represents momentum, is 0, right? The delta P, change in momentum, is 0, and therefore the final momentum minus the initial momentum is equal to 0. And we can also say that the final momentum is equal to the initial momentum. Makes sense? where we know momentum is mv, right? Mass times velocity. We mentioned that earlier. Well, we know that mv, the m1v1 plus final plus the m2v2 final, both equal to 0, right? When we rearrange the equation, we can say that our velocity 1 final is equal to negative mass 2 over mass 1 v2 final. Negative means there's going to be a negative motion, right? Remember we talked about recoil. Recoil is going to happen in the negative direction or towards the left, right? We can then put in the mass of the object 2 on the top. So that's the particle 2, the arrow, over the mass of the object on the bottom, particle 1, the man, 60 kilograms, right? And then what we want to do is we want to specify the velocity of object number 2, which makes up the momentum of momentum 2, multiplied by this ratio of masses, right? The ratio of masses. And when you do that, when you take the ratio of masses and multiply it by the initial velocity across the x-axis only, the I component is the ith component, or the x component only, right? Then we get a value of negative 0.42 meters per second across the x-axis. That's the ith component. Make sense? Again, all we've done is moved around the equation, right? Because we know that m1 v1 final and m2 v2 final must be equal to 0, where m1 v1, right, as an example, is the mass and velocity of the man, right? And m2 v2, right, is the mass and velocity of the arrow, respectively. And we're solving for v1 because we want to know the recoil that we're getting off the man. Simple enough. So the final velocity of the archer is negative, indicates he moves in a direction opposite the arrow. Archer has much higher mass than the arrow, so the velocity is much slower, and that's why we have that ratio. Okay. But the problem seems simple, but could not be solved using the previous analysis models because we didn't have enough information, right? We'd have to have way more information around that. Now we know a bunch of stuff here in this thing that I want to talk about as well, which is he's on a frictionless surface. If this model was not on a friction, if he was on a surface with friction, then we can apply another model or another approach to his motion across a frictioned surface, of a surface with friction. The same thing if I had some kind of other things happening on the x-axis, like a backwind. You know, as an example, there's a wind pushing the archer in the same direction as the arrow. When the arrow is fired, will he move? Or if he's braced in some ways with another mass, and so his mass is bigger than he would normally be, and so on. So we just said it. Our linear momentum then, which is what we're talking about, is big P, right? It's a vector, and it's approximately equal to mass times velocity, right? The velocity vector. So that's what momentum is, what we're talking about. It's a vector quantity because it equals the product of a scalar quantity, mass, and a vector quantity, velocity, right? Its direction is along the velocity components. It has dimensions, right, that we know already. Mass, as example, times speed, or meters per second. L over T means meters per second. So in other words, kilograms per meters per second, right? That's the momentum. How many kilograms of energy, right, do I want to apply across a velocity, right? And that makes sense. If I have the Hulk and he weighs a lot and he's charging, a locomotive, some kind of train, and he's charging at a high speed, rate of speed, and he's really big, as an example, then he's going to have a higher momentum than, let's say, someone like Spider-Man. And the same thing, if we're talking about these superheroes, right? Not to say that Spider-Man isn't strong, and this is where, superheroes and strength and all that stuff are unrealistic, because, even though Spider-Man is super strong, he can lift a truck over his head or whatever, In the comic books you can anyway, as an example. No, I'm not dissing Spider-Man. I love Spider-Man, right? But the thing is, it doesn't make any sense. Spider-Man should have a much higher mass in order for him to lift something like that and not be crushed, right? As an example. And so, some other superhero movies and superhero genre talk about that, where a person can be really, really strong, but if they try and pick up a truck, they're going to rip themselves apart. Okay? Because their body is not strong enough to do it. So linear momentum then can be broken down into its component parts. Here we can break it down into x, y, and z components. So px, py, pz, and the resultant forces is where we said the sum of all forces, as an example, right, is equal to ma. We can relate it to Newton's laws, second law, where mass is times acceleration is mass times or velocity over time. Change of velocity over change of time. And once we know this, right, we can start substituting stuff around. We can say the sum of all forces is equal to the derivative of mass times velocity over time, or we can say that it's equal to the sum of all forces equal to the change in momentum over time. Okay? So that's something we can also relate. Okay, we want to talk about the difference between impulse and momentum. All right. In a momentum of a system, if a net force from the environment acts on the system, right? So, again, from a momentum consideration, a system is non-isolated if a net force acts on the system for a time interval. Example we just talked about earlier, which is on the y-axis, it's non-isolated because gravity is acting on it. Whereas the x-axis, there's no other forces acting on it, so therefore it's an isolated system. Okay? So we can say that from Newton's second law, then, that force is equal to ma, or the sum of all forces is equal to the change in the momentum over the change in time. And solving for the change in momentum gives us that the change in momentum is equal to the sum of all forces times the change in time, or over time. The sum of all forces over time is the change in momentum. So when we think about impulse, the integral of the area under the curve, the time curve, the amount of time that we're applying the momentum, this is called impulse. So impulse is actually the integral of the momentum curve. Okay, that's what it is. So impulse then is a vector quantity having a magnitude equal to the area under the force time curve. Right, so again, let's see if we can get that area. Here's the force time curve, right, as an example. The amount of force that's being placed over a length of time, and depending on how much force is being put in, we can get a instantaneous amount of force at a particular time. This instantaneous time would be the derivative, but we want to find the area, the total force that's been used over the total time, right? We need to take the integral of this, and this is called the impulse. Okay, I'm not going to go into integration right now, as calculus was out of scope for this semester, but that's how we would do it. That's what it means when we say impulse, right? Impulse is not a property of the particle, but rather a measure of the change in momentum over the particle over time. So in other words, I have some kind of velocity that changed actually. Unless the particle breaks up, the mass isn't going to change over time, right? The velocity is going to change over time. That means it's either slowing down or speeding up. If I'm speeding up, this time curve, force time curve is going to look very different. Here we can clearly see that in the beginning, initial time, we have an increase in the amount of force that's being used. Why? Because we're accelerating, right? As we're accelerating a particle into its peak, right, we can see that there's more force that's being used over time. And then what we're doing is we're decelerating. Notice I said accelerating and decelerating. Why? We're talking about force. Mass times acceleration, right? And that's what I'm doing here. I'm indicating this curve is showing us how the mass is being accelerated over time. And we know that as acceleration takes hold, so too does velocity increase. If a velocity is increasing, the momentum is increasing. If the velocity is decreasing, the momentum is decreasing. It's directly proportional. Okay? Clear? So again, impulse can be found by using the time average force, right? So we have the sum of all forces. This is impulse. The impulse vector is equal to the sum of all forces times delta time, right? Which is basically the change in time, right? Sum of all forces times the change in time over time, right? That's equal to the impulse. Sometimes what we want to do is we want to use an impulse approximation, and especially when it comes to analyzing collisions, because you want to say, okay, how much momentum was it at that particular time slice, as an example. This force will be called the impulsive force. That's the impulse approximation, the force that's being used at that particular time slice, right? The particle is assumed to move very little during the collision itself, right? And we can say that the momentum initial and the momentum final represent the momenta immediately before and after the collision. So we're looking at just before and just after the collision in order for us to get this idea of an impulsive force, or the impulse approximation. Okay? Why do we need such things? Because we want to kind of talk about collision response. What's the response to the collision? Here's an example, right? In a particular crash test, a car of mass 1,500 kilograms, right, collides with the wall as shown in figure 9.4. The initial and final velocity of the car are v initial is negative 15 meters per second across the x-axis, so on one component only, right? And the v final is 2.6 meters per second across the x-axis in the positive direction. It reflects back the other way, right, respectively. So v initial, v final, just before, just after. If the collision lasts for 0.15 seconds, so a fraction of a second, find the impulse caused by the collision and the average net force exerted on the car. Again, a really useful piece of information. We want to kind of understand how much force was used on the car right when it hit. Let's analyze this thing. Again, we're going to do the same thing. The collision time is very short, 0.15 seconds. We can imagine the car being brought to rest very rapidly and then moving back in the opposite direction, or reflected back because of the energy that's coming back. Categorize. Assume net force exerted on the car by the wall and friction with the ground is large compared with other forces. All right? Gravitational and normal force are perpendicular, so do not affect the horizontal momentum. It makes sense because they're being counteracted. Normal force is counteracting the gravitational force. The friction is minimal because it's got a car. It's not your car with wheels, let's say. We can apply the impulse approximation because of these factors. The car's change in momentum is due to impulse from the environment. Therefore, the non-isolated system or momentum model can be applied. Okay, cool. Analyze. The momenta before and after the collision between the car and the wall can be determined. Find the initial momentum, find the final momentum, we find the impulse, and then we can figure out the average force. Okay, here we go. So we have we're looking for our impulse vector, right? We know that the change in momentum is equal to the final momentum minus the initial momentum, right? We know this is constant, right? That it's going to be, this equates, this is 0. So we can break this down into mv final minus mv initial, right? So we can factor out the mass. We know that the mass is 1,500 kilograms, and v final is 2.6 meters per second to the right, right? That's on the ith component, minus a negative 15 meters to the left, right? Which works out to be 2.64 times 10 to the 4th kilograms per meter squared. That is the impulse that was generated by this collision. All right? Evaluate the average net force exerted on the car. Well, we know the impulse, and we know that the sum of all forces average is the impulse over time, right? We said the total force over the total time, right? We can say that 2.64 times 10 to the fourth kilograms meters squared over meters per second, over 0.15 seconds, a very short collision time, is roughly equal to 1.76 times 10 to the 5 newtons across the x-axis. So refreshing, Vincent says, impulse is essentially the change of momentum at a moment of collision. Absolutely. Because that's what's happening here, right? That's a total momentum that's happened. That whatever is left over, when we take the final momentum and the initial momentum, and we want to calculate the impulse, the impulse is really the change in momentum. If you think about this, just look at these two things. Impulse is the change of momentum. No time involved here at all, right? And once we find the change in momentum, so the difference between the initial momentum and the final momentum, that's the impulse, if we think about it, in this particular case. And once we have the impulse, we can figure out the average net force exerted on the car. The net force is a combination of the normal force in the car from the wall and any friction, not nay friction, any friction force between the tires and the ground as the front of the car crumples, right? And make sure we check the signs on velocities to be sure that they are reasonable. That makes sense. All right, so when we think about collision then, it represents an event during which two particles come close to each other and interact by means of forces. Now we're going the other way around when it comes to collision, right? It may involve physical contact, but must be generalized to include cases where interaction without physical contact is possible. A good example of that is magnetic forces or field forces that can collide, right? So it doesn't have to physically be connecting. In our cases, because we're talking about games, it's all physical rigid body collisions or soft body type collisions. All right, mostly we're talking about rigid bodies in our cases, right? The interaction forces are assumed to be much greater than any external forces present, right? And this means that the impulse approximation can be used because at that moment in time when it's colliding, those forces are the most important forces that we're looking at, that we're observing. The highest amount of force being used at one time. Here's a collision example, okay? Maybe the result of direct contact, right? So the impulse forces may vary in time in complicated ways, okay? This force is internal to the system, and observe the variations in the active figure. Momentum, again, is conserved. Now here's something that's happening. I have an object, M1, it's moving in towards the left, right? And an object, M2, it's moving towards the right, as an example. So from 1 to 2. And, sorry, it's the other way around. M1 is moving from 1 to 2, this direction, to the right. And M2 is moving from 2 to 1 in the left direction, right? So when we look at that, because M2 seems to be larger than M1, what can happen? Well, if there's a couple of scenarios here we're going to talk about here. All right, so let's talk about different kinds of collisions. Now we're getting into the meat and bones of interesting stuff, right? There are different kinds of collisions. In an elastic collision, momentum and kinetic energy are conserved, right? Perfectly elastic collisions occur only on a microscopic level. Why? Because we don't know of any collision we can see that is perfectly elastic. Why is that? Because perfectly elastic means infinitely elastic, right? Even a ball isn't infinitely elastic, although it's close, right? In macroscopic collisions, only approximately elastic collisions occur, right? In other words, they're kind of elastic, but there's some issues. Energy is lost to deformation, sound, heat. We talked about these things before. Energy moves, right? Because it's not a perfect transfer of energy. Whenever we have a collision, energy is lost in terms, it goes into the environment, right? It's for example, in sound waves or in heat or in sound or whatever it's going to be. And when you crumple an object, a lot of the energy is absorbed inside the crumpling. Of course, we want that so we don't kill ourselves when we collide with other cars. In inelastic collision, kinetic energy is not conserved, right? Although momentum is still conserved. If an object sticks together after the collision, it is a perfectly inelastic collision if they stick together. Why? Because what's happening is I'm carrying forward the other object in the opposite direction, right? It almost like my masses combine at the end. If my masses, if we can think of our masses combining in a perfectly inelastic collision, that's what happens. That's what it's almost like I have one combined mass at the end. Okay? In an elastic collision, those are the ones we normally care about, right? Because it's rare that we have an elastic collision unless the mass is so big, one mass is big and the other mass is really, really tiny. In an inelastic collision, some kinetic energy is lost, but the objects do not stick together in an inelastic collision. We're not talking a perfectly inelastic collision, right? We're just talking an inelastic collision. Elastic and perfectly inelastic, when we say perfect, I'm saying infinitely, right? Elastic and perfectly inelastic collisions are limiting cases. Most actual collisions fall in between these two types, but momentum is always conserved in all types of collisions. Okay, here's some examples. Perfectly inelastic collisions, right? So I have momentum of an isolated system is conserved in any collision so that the total momentum before the collision is equal to the total momentum of the composite system after the collision. Remember, we're combining two masses. Each mass is its own system, if you will, right? I'm combining or making a composite. Once I make a composite, I have a perfectly inelastic collision. So before the collision, the particles move separately. After the collision, the particles move together. This is a perfectly inelastic example. Elastic collisions, on the other hand, both momentum and kinetic energy are conserved. All right. Sometimes, remember, in an elastic collision, kinetic energy is some of it's lost, right? Whereas here, it's all conserved. So what happens is we have a collision response. Again, we can think of this as your momentum initial is equal to your momentum final. Your kinetic energy initial is equal to your kinetic energy final. Once we have these equations in play, right, as an example, we can start solving from one into the other because we're talking about the same velocities, right? M1 and M2, right? We can say that we know that kinetic energy final is equal to 1/2 of M1 V1 final squared plus 1/2 of M2 V2 final squared, right? Both of the masses and the velocities, right? That's the total kinetic energy of the system is going to be conserved. Typically, there are two unknowns to solve, and so you need two equations. Two equations and two unknown. We use a system of linear equations to figure this out. Okay, kinetic energy equation can be difficult to use, but we know that with some algebraic manipulation, a different equation can be used. V1 initial minus V2 initial is equal to V1 final plus V2 final. We know this is the case, right? Why? It can only be used with one-dimensional, so only on the x-axis as an example. Remember, we don't care about the y-axis if the normal and the gravitational forces counteract each other. In the case of a car, this is great, right? Because we don't care about those forces, right? However, if an object is flapping or flying or moving in both the y and the x direction, this can't work, right? So one-dimensional elastic collision. It doesn't have to be perfectly elastic between two objects. Using this equation eliminates the need for using an equation with quadratic terms from the kinetic energy equation, right? And this makes it much easier for us to figure out the final stuff. So if I have the initial velocity, as an example, if I have 3 of these knowns, right? And I want to find out the fourth one, it's okay. I can figure it out because I have enough information to do this. I can isolate one of the terms, and I can figure out either the final velocity of the second object or the final velocity of the first object if I know 3 of the other things, Pretty simple. And it's showing this right here. Suppose the masses and the initial velocities of both particles are known. Well, then what we can do is, once we know this, right, it's just, all it's doing is deriving the equation, right? We can remove the velocity, the masses, and once we remove the masses, we can, you know, reduce it to what the equation. Okay, special case 1. If M1 is equal to M2, this is special case 1. If both masses are the same, the particles exchange velocities. That's what happens. So again, if we had two cue balls, or two billiard balls, right? But two billiard balls hit, because they're approximately the same mass, right? Then they exchange velocities. One goes in the direction of the original ball, and the other one goes in the direction of the first ball. If the one ball wasn't moving, the first ball stops, and the other ball, it transfers the energy to the second ball. Okay, kind of how it works in real life, with some variation in results, because not all billiard balls are created equal. They're very close, right? But they're not perfect. Okay, does that make sense? That's case number 1. This is important because if you make the masses the same for objects, right, then this is a great way. We can finalize this very quickly. We swap the velocities. That's all we're going to do, right? And this is great for a game. We don't have to even think about stuff. We just say, you know, we want to do a swap algorithm, and we're good to go, and it'll look realistic. All right, special case number 2. If M1 is much greater than M2. Okay, in this case, when a very heavy particle collides head-on with a very light one, big mass and small mass, initially at rest, the heavy particle continues in motion unaltered, and the light particle rebounds with a speed of equal to about twice the initial speed of the heavy particle. Which means if let's say a massive particle is traveling at 10 meters per second and hits a small particle that's not moving, right, at rest. Now that small particle rebounds from the first one in the same direction that it's going, and it goes 20 meters per second. That's kind of a case. Here's another one. When a very light particle collides head-on with a very heavy particle at rest, the light particle has its velocity reversed, and the heavy particle remains approximately at rest, doesn't move, because it's so massive, right? This, my friends, this case 2 is directly working for your assignment number 3. If you think about the wall as an extremely heavy particle, then what's going to happen is the ball or the object is going to bounce off the wall, and the energy is going to be reversed. That's what's happening. That's why it's special case number 2. Okay, we're talking about collision response, and this is in line with what we've been talking about. All right. And again, we can conceptualize, you know, as an example in our minds. I'm just going to go into the next scene here. I'm going to skip by these to go to the next thing here so we can save some time. Okay, so imagine here's a stress reliever, right? Imagine one ball coming in from the left and two balls exiting from the right. Is this possible? Well, due to the shortness of time, the impulse approximation can be used because it's only going to be hitting the ball very minimally, right? We categorize the system as isolated in terms of both momentum and energy, right? And we can think about the entire system as using elastic collisions. Each of the balls are approximately equal in size, right? So do you think it's possible that I can get two balls to the right if I only have one ball entering from the left? So let's check to see if momentum is conserved. It is. Let's check to see if kinetic energy is conferred. It is not, right? Why? Because the kinetic energy, it's not perfectly elastic. Therefore, the collision couldn't be elastic. If it was, it'd be. If the collision was elastic, then the kinetic energy would be conserved. Finalize. Having two balls exit was not possible, right? If only one ball is released, because of this problem. Because somehow the kinetic energy would be double. There's no way that could happen. So therefore, in our mind, because this is the case, this is not possible. Because we know that from the system itself, right, that this is an elastic collision. So we know it can't be two balls. It only must be one ball. So one ball hits. the energy is passed from one ball to the other until it gets to the last ball, right? From one system to the other, it's transferred until the final ball happens. And because they're all equally rated, right, then this one is going to leave while this one stops, because this one is stopped. This is case 1. Okay. All right, and it talks about that in here in more detail. I'm going to skip these. If you're interested in looking at that, you can. Here's a collision example with a ballistic pendulum. All right, so observe the diagram. The projectile enters the pendulum. So there's something that's hanging. A block of wood is hanging from the ceiling. Some kind of bullet, a projectile, enters the pendulum. Okay, enters the pendulum. In your mind, what kind of system is this? Is this elastic or inelastic? What do you think is going to happen? Before you read on, what do you think? If the bullet is entering the pendulum, right? So I've got a block of wood. The projectile is entering the block of wood. Unless it exits the block of wood, right? And even if it does, what do we have? We could have an inelastic collision, because the systems are going to be it's going to be a composite system at the end. Let's take a look if we're right. So again, the isolated system in terms of momentum for the projectile in the block. Yes. Perfectly inelastic collision. The bullet is embedded in a block of wood. At least that's what we've been told. You can see the diagram here, right? Momentum equation will have 2 unknowns. Use conservation of energy from the pendulum to find the velocity just after the collision, right? And then you can find the speed of the bullet. Okay. Here's something, this is what actually a ballistic pendulum really looks like in real life, right? Where you have some kind of projectile hit the pendulum, and it's going to be a perfectly inelastic collision. It's going to move together as one. All right. So far we've been talking about one-dimensional collisions. Collisions where we don't care about the other dimension, only on the x-axis is an example. We don't care about stuff on the y-axis. Why? Because the y-axis is countermanded by the normal force and the gravitational force. Okay, but in 2 dimensions, what we want to do is use subscripts to determine the velocity and the mass across different axes. So for example, m1v1x and m2v2x is equal to m1v1 final x. This is initial x. This is final x. We know that this is true, right? And we can separate or decompose the momentum across both axes. Okay, so here it is. So here's a case. Particle 1 is moving at a velocity v1 initial, in some velocity, some trajectory, whatever that is, right? And particle 2 is at rest. There we go. Okay. In the x direction, the initial momentum is m1 v1 initial, right? And in the y direction, the initial momentum is 0, because here we don't have any up and down motion in this particular case. After the collision, the momentum in the x direction is m1 v1 final times cos theta, all right, plus m2 v2 final plus cos phi. Why is that? Well, because notice that they're offset. Okay, it's not a head-on collision. We're getting part of the energy transferred across the y-axis and part of the energy transferred across the x-axis, because you're hitting it at an angle, right? So what's going to happen is, when we apply cos theta and cos phi, depending on the angle of attack, how much angle there is here, right? We're going to have an angle where one object goes in one direction and the other object goes in the other direction. Really depends on the angle here from the horizontal. So how much offset it is. And the masses of the object. So after the collision, the momentum in the y direction is m1 v1 final sine theta and minus m2 v2 final sine phi. Okay, that's the direction in the y-axis. The momentum in the y-axis, because momentum is conserved. If the collision is elastic, we apply the kinetic equation, energy equation. If in this example, this is an example of a glancing blow or a glancing collision, where things glance off each other and bounce, almost like reflect in some ways. So we conceptualize. We imagine the collision. We predict the approximate direction of the particles we'll be moving after the collision. We draw it out. We set up a coordinate system and define the velocities with respect to the system, right? And then what we want to do is, when we categorize it, is the system isolated or not? And if so, we categorize the collision as elastic, inelastic, or perfectly inelastic. Those three options. We write the expressions for the x and y components separately, right? And then what we do is we write expressions for the total momentum of the system in the x direction before and after the collision, and then we repeat the same thing for the total momentum in the y direction, right? Once we have that information, we know that momentum is conserved across both coordinate spaces. All right, here's another one. A 1,500 kilogram car. We got some values now. A 1,500 kilogram car is traveling east, this way, right? With a speed of 25 meters per second, so across the x-axis, right? And collides at an intersection, somewhere in here, with a truck traveling north, 2,500 kilogram truck, a bigger object, traveling north, right, at a speed of 20 meters per second, slightly smaller speed. Okay, momentum. We know that just by looking at the values here that we've been given. Let's do a quick calculation here. So if I was to do that, if I said, let's calculate the momentum just on the x direction, as an example for the, where is that thing? Oh, it's right here. If we calculate the momentum of, we're going to talk about units of the car. So 25 meters per second multiplied by 1,500. We have, in terms of units, 37,500 units, right? So kilograms per meter squared. Okay? 37,500. What about the truck? Well, we know that 20 multiplied by 2,500 is 50,000. Guess what? There's more momentum going across the y-axis up than there is across the x-axis to the right, which means I'm actually going to go to the right in this direction, right? And because why? It's going to go more forward than to the right. Why? The mass of the car is much smaller. Well, we're not quite half, but let's say almost half of the mass of the truck. So the truck's momentum is going to carry the whole system forward in the north direction. We know that that's going to happen. It's also going to move a little bit to the right, right? Because there's momentum happening on the x-axis, and momentum is conserved across each component. Okay. Find the direction and magnitude of the velocity of the wreckage after the collision, assuming the vehicles stick together. Sticking together, this whole mess is a perfectly inelastic collision. Because it's a perfectly inelastic collision, we want to look at the composite system at the end. So again, we look at the components. We ignore friction. We haven't been given that. We model the vehicles as particles. We model the system as isolated in terms of momentum, and the collision is perfectly inelastic because the vehicles stick together, right? Then we can use the equation that we've been given, such as the change in momentum on the x-axis is 0, and the change of momentum of the y-axis is 0. And when we solve everything, we break down the equations. We have two equations and two unknowns. Okay? And we can see here that we have, we can sub in the numbers. We know the mass and velocity initial. We know the mass 2 and velocity initial. Once we know those two things, we can multiply it by, we want to get the final velocity, right? m1 plus m2 v final times cos theta, right? When we're adding the masses together, why? It's a perfectly inelastic, it's an inelastic collision. It's an inelastic system. We're getting a composite, right, at the end. All right. So, and this is easy to calculate because in this case, the car had no lateral values. There's no x component here, and the truck, I mean, and the car had no vertical, components at all. It only had a horizontal component, an x-axis, right? So there's no, up and down motion like north-south motion. This has no east-west motion. So therefore, we've just isolated it on the x and y axis. It's kind of a very simple problem. So when we start subbing things in, we can see that divide equation 2 by equation 1 because we want to solve, right? We want to kind of combine the two equations to get a ratio, and we want to find the angle of attack. The first thing we want to do is we want to solve for that theta, whatever that theta is. Sine theta over cos theta, or y over x, is going to give us this tan theta. We know this is the truth. When we solve for tan theta, we get, after we sub in the numbers, right, the arc tangent is going to give us 53.1 degrees based on the numbers. Once we have 53.1 degrees, use the equation 2 to find the value of the velocity final, because we can't find that out without subbing in the angle of attack, right? So we take in the mass 2 times velocity 2 over mass plus mass 1 and mass 2 on the bottom, the ratio of masses at the bottom, right? Times sine theta, and we're getting this equation here where we know that it's going at an angle of 53.1 degrees to the right, plus 15.6 meters at a velocity of 15.6 meters per second. Okay, that's the total velocity. Velocity final, the velocity vector. Notice the angle theta is qualitatively in agreement with the figure above, right? And we want the result to be consistent with the kinetic energy of the system being reduced in an inelastic collision. Okay. So that's kind of examples. Let's talk about something called the center of mass. So there's a special point on a game object or a system called the center of mass, right? As an example, that moves if all of the mass of the system is concentrated at that one point. A lot of times what we want to do is we use the center of mass. When we look at a particle, even if it's a big car or whatever, we always look at the center of mass to determine where the particle is, right? Kind of where, if we're going to balance off the mass, that's kind of the average mass of the mass is, we can say, is coalesced at that one place from a model perspective. Okay. So I want to find the coordinates for the center of mass, right? And we can look at mass 1 and mass 2. When we combine two masses, right, where is the space? Well, depending on how much mass is on the right and how much mass is on the left, we're going to get, if there's more mass on the right than on the left, then obviously the center of mass is going to be towards the right, because more of the mass of the entire system is going to be towards the right, in this case, where you have a heavier mass on the right and a lighter mass on the left. Okay. Whereas on the y-axis, it's going to be perfectly centered, because we're colliding. This whole system is colliding, as an example, and there's no vertical motion here in this case. All right. We can also call something an extended object. So where we have a distribution of small elements of mass delta m initial. I have a bunch of little elements, and I want to find the center of mass. And by the way, when we start talking about this is kind of a little bit out of scope for what we're doing here in our game examples, because a lot of times it's not like we have a bunch of little things that combine to make something bigger, typically. Okay, it's more like the other way around, where we have a big object that breaks down into smaller pieces. That, no problem. But this idea, or masses that are irregular, right now we've been talking about a regular rigid body. If we have an object that's soft body, right, irregularly sized, then we want the center of mass gives us a lot of information. And sometimes for irregular masses, we might have two centers. Okay? Here, we're just going to talk about it very briefly. And I'm going to skip over this part because we really think about the center of mass of a symmetric object for the most part. The center of mass of any symmetric object of uniform density, this is another thing. We got to think about how much density there is in an object, lies on an axis of symmetry on any plane of symmetry. In other words, in the middle, right? How about center of gravity? Each small mass element of an extended object, when we think about an extended object, means that there's more than one, right? Is acted upon by the gravitational force, right? So if you have an object, a composite set of objects that are all together, each of those objects are force or gravity is acting on everything, not just on one thing. Here's an example of that composite, scenario where I have two objects in a system as an example. I'm not going to talk about this because it's like a pulley, and we don't really want to think about a pulley in terms of what we're doing here today. How about the center of mass of a rod? That's different. Okay, so find the center of mass of a rod of mass m and length L. Okay, that's pretty simple. Here's a question: is the rod itself, is it connected to a wall or not? If the rod is not connected to the wall, then the center of mass would be pretty much in the middle of the x-axis. The object, the length of the object, that would be the center, right? Again, this is in a perfectly shaped rod with equal density across the entire thing, where density is the amount of molecules or mass across the rod. For example, if I had a density that was higher on the right side, then there's going to be more particles, which means a heavier mass on one side than the other, and therefore the center of mass would veer towards the right, towards the amount of particles in that one area, as an example. And a good example of that is if I'm holding a weapon, right? So imagine if I'm holding a weapon, a rod, where my amount of density on the rod itself, I have a bigger, kind of an irregular mass, not a symmetrical mass, but something like, let's say, a heavier mass at the end of the rod. An example would be like a morning star, or some kind of mace, or a maul, like a hammer, or something like that, where I have a lot of mass at the end. The center of mass cannot be in the middle of the rod, the handle. It's got to be towards the end. That's where the center of mass is. And that's why when you swing an object like that, you're going to get a momentum based on where you're holding it. It's really, really important. All right, I'm going to skip this over because, again, this is outside of our stuff. So, motion of the center of mass. A projectile is fired into the air and suddenly explodes. With no explosion, the projectile would follow the dotted line, right? After the explosion, the center of the mass of the fragment still follows the dotted line. This is interesting. The same parabolic path the projectile would have followed with no explosion. But you have particles also streaming in another direction, and usually in the x direction or whatever, and it's going to be affected by the explosion, right? So keep that in mind. So that's how it's going to look. This is really relevant for us. So we have something that explodes in midair or gets hit in midair, but some particles are going to continue to rain down where they're heading. This is why if we intercept a missile or some kind of particle in midair that's heading towards the city's going to still have some particles rain down on it. Why? Unless we completely obliterate the object that's coming down, especially if it's a heavy particle that's made up of a lot of mass towards a city, like let's say an asteroid or something crazy like that. Unless we completely obliterate it, different pieces are going to fall on the same trajectory that it's going into. Okay. Again, these are all extra topics that we can talk about. Rocket propulsion, right? When an ordinary vehicle are propelled, the driving force of the motion is friction. Why? Because I'm using the car to push the road away. That's what's happening, right? But the operation of a rocket depends on the law of conservation of linear momentum as applied to an isolated system, where the system is the rocket plus is ejected fuel. So this is where the rocket science comes into play, right? I'm losing fuel. Because I'm losing fuel, my mass is not constant. Because my mass is not constant, right, then what's happening is my momentum is changing. Momentum is changing because my mass is not constant anymore, right? Again, I'm not going to talk too much about rocket propulsion, but the idea behind it is very interesting. At the end, though, what's going to happen is if we want to find out, how much more propulsion is needed, as an example, after there's, the fuel is being expended, that is a very challenging equation to solve. Rocket science. Okay, we're going to move on. Thrust on the rocket is the force exerted on it by the ejected exhaust gases. Okay, so to make it simple for us, as an example, and unless you want to make an actual simulation or something, and I'm just talking for games here, right? What we want to say is that thrust it's going to be proportional. The amount of momentum is going to be proportional to the amount of mass that leaves the system. That's the easier way to think about it, right? That's not true, actually, right, in real life, because as the rocket loses fuel, then you're actually going to have a different state of momentum. But for the most part, the thrust increases as the rate of change of mass increases, right? Because as the rate of change of mass goes down, the thrust increases. Notice when we actually fire a rocket, how it gets faster and faster. Why? Because the same amount of propulsion is driving less and less mass over time, which means it's going to accelerate. The rate of change of the mass is called the burn rate. How much fuel I'm eating up is the burn rate of the rocket, right? Kind of a neat idea. Neat, but again, out of scope of what we're talking about here in this course. All right, finally, we get to the really cool stuff, the collision response. All right, we talked about momentum and impulse, and those are really great things. And we talked about things like conservation of momentum and conservation of kinetic energy, elastic and inelastic systems, right? These things you need to know when you look at your assignment, right? Think about, classify what they are. Is what I'm asking for you to do elastic or inelastic? What do you think? Both assignment parts, 1 and 2, right? Is it elastic or inelastic? What am I looking at? Can anyone answer that question? Vincent says elastic. Yeah, for the most part. But here's something to consider, right? If I'm moving my brick, and the other part of the assignment, if the ball hits the brick and I move it quick enough, would I not be pushing the ball and the brick at the same time? If I am, then we're combining. We have a composite system that's moving together for a brief time. And so we can say that for that moment in time, it's inelastic. Again, think about this. If I'm moving my finger and I'm moving the brick with my finger or my mouse or whatever, and the brick is moving at the same speed as the ball that's hitting it, right? Then it becomes inelastic, right? Because one system is coalesced into, or two systems have coalesced into one, right? I'm carrying the ball with you, exactly, to stop the brick, and the ball carries the velocity over, exactly. And that's why if I move it really quickly enough, it's different if I bounce it and push it back, a really quick little a collision. But if I carry it forward and if I go fast enough, if I kind of move almost like I'm swiping the ball with the brick, right, as an example, then now it becomes a different kind of thing. Think about tennis. Is tennis perfectly elastic or is it inelastic? You want to say elastic because the racket is going to project the ball or reflect the ball in the direction that the tennis player wants. Okay? But it really depends on how the racket is swung as well, right? Because the racket, especially the velocity of the racket, it could almost be in some cases it's not realistic to say it's perfectly elastic. It's not. There's going to be energy loss. There's going to be sound, especially with how the complexities of that. As an example, it can mean that for some point of time, a small amount of time, that the masses combine just for a small amount of time, which means there's some inelastic component to it. Again, outside the scope of this course. We want to think about it. We want to model it in our mind as elastic. Same thing with a golf ball, a golfing example. We hit a ball with a club, right? Then we want to think about it as elastic as much as possible. All right. Here's collision response number 2, part 2. So we normally, we've gone about halfway. We made it somehow close to halfway. More than half of the slides are done. I think we're doing well in terms of time frame. Let's continue and see how we go. All right. So let's think about this. Bouncing off horizontal or vertical walls. That's what's covered. Bouncing off incline walls. Collisions between particles in 1D. Collisions between particles in 2D. All right? Let's talk about bouncing off horizontal or vertical walls, okay, which is part of your assignment. All right, so we'll look at how to make a ball bounce off a straight wall that is either horizontal or vertical. In a 2D simulation, space is a floor, ceiling, or room wall. For illustration, we're going to use a vertical wall here, but similar principles will apply to horizontal walls as well. We'll look at elastic and inelastic bouncing in turn, bouncing in which the kinetic energy of the ball is or is not conserved. Let's think about that. Again, we know that kinetic energy is 1/2 mv squared, and this applies to the velocity of magnitude is changed by the collision. All right? So here's an example. Consider first a special case in which the ball hits the wall perpendicularly with velocity v. So that means it hits the normal basically. It's going across the path of the normal to the wall. All right. In that case, it's going to bounce back perfectly the other way around. Again, if this was a perfectly elastic collision, which is what we're thinking it's going to be, then it would just be reversed minus v, which is what I'm telling you to do with both the x and y axis. We just reverse the component where it's going. So if it's going at a velocity rate on the x-axis, we just reverse the x-axis and go the other way. Y-axis wouldn't be changed. But there is a case sometimes where, depending on the number of frames, what happens is, as an example, whenever we check, that there's going to come a case where the ball, when we check to see the collision, is going to be through the wall. What we have to do, it's going to penetrate it slowly, is reposition the ball on the other side. So where it would go in, we want to reposition it here before we show the visual collision, right? Otherwise, it's going to look wacky. It's going to look like it went into the wall and came back out again. So repositioning is necessary, not just to avoid the visual effect of the ball penetrating into the wall, but also because the problem of the ball getting stuck in the wall, which can happen, right? And the latter situation might happen if the reverse velocity of the ball is not sufficient for it to get out of the wall. Especially velocity is also reduced to account for some kind of energy loss. So we're going to talk about energy loss, because remember, you got to think about every time step or frame that we're looking at it. Okay, so let's draw this out for a second before we continue with this example, so that way we're clear. So here's the scenario. All right, so I'm going to give you these time slices. Let's suppose I have these time slices. I'm trying to make them as even as I can. And each of these lines that I'm going to draw as much as evenly as I can with my eye, they're approximately, let's say that's not right, but they're approximately the same number of frames, the same frame length. Okay? And let's just say that this is the last one. Okay? And let's suppose a ball is moving at a rate of speed that's going to carry it through the wall. So when we initially place the ball is here on this part of the frame, and it's going to move here, 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 and at the end, if we did it right, then it would move approximately here. Sorry, the ball is slightly different, but bear with me. Okay, so this is where it's going to be. Great. Well, what if, even though this is the frame rate of the ball, what if the wall is not at the edge, but rather the wall is here? That's what we're talking about. Where we're checking here, so this is where we're checking. Oops. Sorry. That's not right either. There we go. We're checking here, and the next time we're going to check is here, to give you an idea. it's going to penetrate the wall. Well, we need to reposition it, right, from one frame to the next, right? Otherwise, what's going to happen is it could get stuck. That's what it's saying, especially if this wall was much thicker, right? It may not have the momentum or the energy to come back out, right? So one of the jobs we have is to say, okay, we've got here, and then how much do we have to move it back before we start reflecting it back out? We have to account for that, all right? So this is the example. So we have, here's my collision detection. Ball.x is greater than wall.x minus the ball radius. Collision detection. Okay? If this is true, the ball is inside of the wall. If the ball is inside of the wall, this condition is true, then reposition the ball at the wall edge. Right? So ball x now is equal to the wall x minus the ball radius. So it's going to be exactly where it's supposed to be. Right? However, then you want to reverse the ball's velocity from that point. Okay, this is where there's no energy loss. Okay, does that make sense? So again, I want to reposition it and collide from there. I don't want to let the ball collide in the wall. So guys, when you do your collision detection, right, you need to employ this formula. Otherwise, you may have challenges when it comes to colliding with the walls in part 2 of your assignment 3. Make sense? Okay. How about if the ball is hitting at an oblique angle? So I've got some kind of angle this way, and I want to bounce the other way. Well, we have to do still the same thing. We still have to reposition the ball, right? And we got to think about what's happening here, right? The ball is has two forces acting upon it, right? We have two energy across the x-axis and energy across the y-axis. If the ball is hitting a vertical wall, right, a wall that's going up and down, then what's going to happen is it's going to reflect across the horizontal, which means the x-axis, whatever the energy is that's happening across the x-axis, is going to be reversed. Okay? However, the energy across the y-axis is still going to remain the same, given that there's no energy loss. Okay? So if there's no energy loss, what's going to happen is we're going to have to reposition the ball back out and back. Not only out one way, but back along its trajectory. So that way it doesn't stick out. We don't want it to stick out this way. We want it back colliding where it's supposed to collide, somewhere around here, right? Because that's where it's going to collide, right? Or here, as an example, where it seems to be touching the wall, right? This way. And so the trajectory changes there. And it talks about that. We need to reverse the perpendicular component as before and leave the parallel component unchanged. Okay. So this technique of decomposing the velocity vector into a normal, perpendicular, and parallel tangential component with respect to the wall is entirely natural for this. But its application can be more general. All right. In other words, it can work in other cases as well. All right. If you need to be extra accurate, there is something else you need to worry about. And it's related to step 2 when we reposition. In the previous code, reposition the ball by moving along the x-axis only, right? But when the collision is oblique, the ball's real position at the point of collision is along the line of collision, or the angle of attack, if you will. So the ball also needs to be moved a little along the y direction, backwards, right? And so let's think about this, this energy that's happening. All right. Let's talk about energy loss. So if we think about energy loss, then, right, there's no loss of kinetic energy in the first example. It's perfectly elastic. But what about inelastic bouncing, or bouncing that you have energy loss, which is what I've asked you to do in your assignment number 2, right? If your energy is being lost, then we have to account for how much energy is being lost when we hit the wall. Okay? So all we have to do is multiply the velocity of the ball normal to the wall by a factor of less than 1. If it's 1, it's perfectly elastic. If it's less than 1, it's energy loss. Okay? The other way to do this, I have to talk about this as well, is what about when you just like how Alex does some kind of friction when we move stuff, he does like this little trick. He calls it a cheap trick when he multiplies the velocity by 0.99 and it kind of continues to slow down and slow down and slow down. That's a way of doing it, but really at the end of the day, it depends on the there's energy loss because every step of the way, right, there's some kind of friction that's slowing the ball down. In the case of assignment 3, part 2, that is what we're asking. We're saying slow the ball down as it goes, right? When it hits the ball, it's going to have energy loss. And if it keeps hitting the walls every single time, it's going to keep losing energy until it stops. So how do you do that? You can take the ball across the x-axis and move it and multiply it by some kind of factor of energy loss. And it's a normalized value between 0 and 1. The lower the value, the more energy loss it's going to have. The higher the value, the less energy loss it's going to have. This V factor, if you will. And you can experiment with this and so that it reduces the energy over time. Okay? We can also think about this as wall friction, right? So or we can also think about this as restitution. How much the wall is going to absorb energy when the ball hits it. This idea of the reversal on, let's say, in the perpendicular but not tangential. Okay, so we talked about energy loss. Let's think about incline walls and how that can work. So we talked about walls that are horizontal or vertical. That's the simplest case. But what about incline walls? That's going to be more challenging because the incline is not on the x-axis or the y-axis anymore. So this presents a bit of a challenge, but what we can do is we can perform something called coordinate rotation, where we adjust or for the coordinate space of the incline. Okay. Example would be if this is the incline, and if the ball is going perpendicular or it's going to hit it at a normal, it's going to bounce back the other way across its normal, whatever the normal is. Okay. So Vincent says, so just scale down velocity to simulate energy loss. Yes, that's the simplest way of doing it. From game physics perspective, right? If you want to be super realistic, then you would have to consider how much momentum you're going to lose, right? By, this inelastic type of collision, right? But from a game perspective, we don't want to necessarily be always super realistic. We want to make it playable. So again, I always, when I look at things, I always look at things like, realism versus playability. Right? The more realistic you are, the less playable something becomes. I always think about this in terms of every game system we ever make, right? I talked about this, Vincent, by the way, and thank you for asking that question. So we can talk about it because this is perfectly related to what we're saying here, which is, think about this, guys. If I make a desktop role-playing game, like I said before, and I want to make a system where every time we hit a piece of armor, or every time we hit, the weapon gets hit, it gets hurt. This idea, it gets hit, it gets hurt, right? That means I'm chipping away at the weapon every single time. If it's, if it's really encumbering, that means I have to, replace my weapons all the time. And I'm thinking of things like back to Oblivion or Fallout, or anywhere where your weapons degrade, okay, as an example, right? When you think about those old games, it didn't degrade right away. It took time for it to degrade, right? But it still degraded at a rate where it made you buy stuff. It made you go back to the stores and pick up new equipment or try and repair it or something. It became a mechanic in the game, right? In real life, if you were trying to mark down how many times your weapon got hit every round, if I was playing Dungeons and Dragons and every time I rolled and I hit an object with my weapon, I wrote down a nick. I marked down a nick, like a tally, for how many times my weapon got hurt. And if after 10 times I lose a -1, right, in terms of a modifier to hit, right, that could be really extreme. It might be realistic because weapons degrade over time. but it may not be fun and playable. So this is the example. So going back to what I said before is, how fun and playable is your game? Super realistic might make it less fun and playable. And another good example of that is platformers. When we create a platformer, and if we use regular gravity, a gravity scale, right, as an example on a platformer, the gravity scale will appear to be, we can say, like the object is floaty, right? If we use regular 9.8 meters per second. And usually we want to try and increase the gravity scale for an object by 3 to 10 times in order for us to get the right amount of gravity. So it seems like when an object goes down, it goes immediately back down, up and down, right? So it's more snappy when it comes to how it works. Is it realistic? No. Can Mario in real life jump 3 times of his height? No. If he was a real guy, probably not. He'd be like a superhero, right? Is it playable? Is it fun? Yes. So we sacrifice realism for playability. And the same thing goes here. We want to sacrifice realism for some playability and for some easy calculations for a development perspective. Still looks like realistic, but not super realistic. All right. So what we're trying to do here is, in the following diagram, P1 and P2 are the position vectors of the endpoints of the wall with respect to the origin, right? And what we're doing is, it depends on the angle of attack. Notice that the angle of attack, if it's not, kind of normal, like completely perpendicular to the surface, we need to calculate the new angle. That's what's happening here. That's what they're doing here with this thing. But the easier way to do that is to rotate the coordinate space to make it seem like the wall is not in itself inclined, but rather the whole coordinate space is inclined. What would happen if this wall was on the x-axis, is what we're going to say. And so we can figure it out that way. Okay? And that's what we would do, as opposed to try and use an equation to try and figure out what the actual angle of attack is relative to the wall. And then you're going to bounce, as an example, we're going to carry forward that angle of attack. It's going to continue the other way around. So the on the x-axis, as an example, if this was part of it would be reflected this way, and part of it would be reflected on the y-axis, because this is on an incline, as opposed to if it was on the horizontal, on the vertical. Horizontal and vertical, you just reflect the other axis. And so what I mean by that is part of what I talked about with other people when I talked about this assignment. Let's talk about this again. So, and it talked about it really briefly. Let's suppose you have the game, okay? And I have a ball that goes this way, and it attacks the wall this way. In this scenario, what's going to happen is the y-axis isn't being impacted at all, right? So y remains the same. Y, the influences on y is just the same. Y and y stay the same. However, x in this case, because it's hitting the right side of the wall, is going to be reversed. So x is equal to negative x, right? Because it's hitting the right side or the left side. Whether it's this side or this side, it doesn't matter. Y is going to remain the same. The y component is going to remain the same, but the x component is going to be reversed, which means that, going with that same idea, that this part is going to go in the opposite direction. Whatever force was going this way, it's going to look kind of like this, right? It's kind of the same angle on this side. It's going to be the same angle on this side. Okay. How about on the horizontal, on the kind of some kind of horizontal surface? This is a vertical surface. On a horizontal surface, you're going to have the same idea, but the other way. So in this case, it's going across the x-axis. It's traveling this way across the x-axis. So the x-axis is going to stay the same, but the y-axis is going to be reversed. Okay, that's what's going to happen. And this is going to be the same for the top or the bottom. Okay? Given this, if we rotate the whole coordinate frame by x number of degrees, all we need to do is rotate the angles that we're going to bounce with that number of degrees. It's the same thing. if we can you know, kind of shift back or account for the rotation of the angle of the plane that we're hitting, if we can account for that angle of the plane and compensate for it, we can still apply this same principle, right? That's what this is saying. Okay, I'm going to move on. And it talks about how we're going to be able to do the same thing when it comes to collision. And it talks about how to do that. We can subtract. In pseudocode, they can be written as follows. Ball to wall 1 is equal to wall, right? Position 1. And we subtract ball and position 2D. And this is kind of the way it's going to work. It's exactly what I just wrote above. Okay. One thing that we have to do is also we have to position the ball, and we have to also consider the case where the ball is in the wall, right? So in this case, if the ball is in the wall, right, then again we may have to position it back here, further back. And I'm not good at drawing this ball. Let me undo that change. I'll just draw the ball and position it myself. Yeah. So let us do one of these. So again, what I mean is, imagine the ball is traveling here and it's going to go into the wall, right? Like we said, what we want to do is we want to come back to here before we collide. And now we're not going to go on this angle of attack. We're going to collide from this place. And it's going to go still across the same thing. So we're going to collide earlier. It's going to go over here, right? So the ball doesn't sink into the wall. That's the idea behind it. Okay, so the repositioning has to happen. And we talk about the repositioning here, and this is what it's talking about here. Now, one thing to note is on an inclined wall, that where it becomes more challenging again. The same principle applies. And so what they do is they use the differences in terms of its trajectory. So we're going to say, okay, here's its trajectory as it's hitting the wall. Wherever the point of contact is, you want to take the ball or the particle from where it hit, bring it back to that frame. Okay? Bring it back there. That's where you're going to collide from. All right? Same idea. Now, it really depends on how fast this thing is going. You may want to always peek ahead with the particle, right? Because if you don't peek ahead with the particle, what's going to happen is it's going to be too late. It's going to look really wacky. Okay. I'm not going to go too much into this right now because really that's what we're talking about. So, but here's the pseudocode for the displacement effect, right? So the displacement, we're going to look at the particle's velocity as an example, and we're going to get the displacement is going to be a factor of the delta angle, if you will, how much it went through. And then what we're going to do is we're going to reposition it across we're going to pass in, we're going to subtract the displacement, again, this is just pseudocode, from its original trajectory. And it talks about how to calculate the tangential velocity as well as the perpendicular velocity, how it does that. And we want to take that and we want to calculate the new velocity that it's gonna take across, you know, given that this angle, the incline is not you know, kind of horizontal or vertical. I recommend using one aspect depending on how much how horizontal or how vertical it is. If it's more than 45 degrees from the horizontal, use a vertical adjustment. Okay. If it's less than 45 degrees, use the horizontal adjustment. All right. In other words, rotate the whole coordinate frame to the horizontal. That's much easier than trying to calculate things this way. We want to adjust things that way, like you normally would. Okay. So you rotate the coordinate frame, make your calculations, and then rotate it back. That's what you're doing. Okay. Basically, that's what the rest of this says. I'm not going to go too much detail, but it gives you a bit of a check bounce equation with pseudocode. All right. And this is the check bounce equation for your incline wall. All right, summary. Let's talk about what we talked about before. I'm not going to go into too much detail of this, but really what we talked about so far is we want to, here's the steps: detect collision, reposition the ball, calculate the new velocities just after the collision. Those are the 3 steps we have to make. But this part is forgotten or not even thought about by beginners, and this is why we're talking about collision response right here. Okay, that's it. We've covered 107 slides out of 119, and I guarantee you that we're not going to get much more detail than that in here from a 1D perspective. So this is, what about particles colliding against each other? So we've talked about static, a particle that's dynamic against a static object. What about particles that are dynamic? 2 particles hitting each other. What about them? And this is where we can get into the place where the particles, if it's just exactly hitting each other, like 2 particles hitting each other, and they're going to bounce back the other way around, as an example, the challenge is how much penetration you have by the particles themselves. And this is generated by the time of collision, as an example, and how much you need to reposition both. Okay, because it's going to be obviously further back, somewhere in between, which is where it's going to happen. So half of L here in this case, if they're traveling at the same rate of speed. If one particle is traveling faster than the other one, then the position of the bounce is going to happen towards the right. And let's say, for example, if this particle is bouncing or moving faster than this one, right? It's going to be moving towards the right. If this particle is moving faster than this one, it's going to move towards the left, where you're going to do the bounce, right? As an example. One challenge that we have with small particles moving at a high rate of speed is known as the tunneling effect. So we talked about this we've been talking about this the whole time, really. So this idea is easy, but what about when, let's make that particle again. So, no, we'll make a particle that is kind of roundish. How about that? And actually, how about we make the particle first? How about that? All right. Vincent says tunneling is like the particle passing through another object if the velocity is too much, right? Yes, it is. So here's the particle, let's say, and we're also going to draw the object. Let's say we're going to draw an object like that looks pretty big, like this, right? And we're going to grab the particle now. So we're going to say that let's grab this particle. Let's try that again with some kind of other thing altogether. No, I didn't do it. I wanted to make it so that it is one of these. Sure. So let's suppose I have this object, right? And I want to move it around. So here I am. Imagine if the particle's moving and I check here, and the next check I check is here. Right? It didn't collide because it didn't get close enough to collide. It was like way out here, let's say. And it's moving so fast and it's so small that it's going to be over here the next time. So it's going to seem like it went right through, right? And the reason why it's going to seem like that is because it's the rate of how many checks you're going to do per frame, right? Remember, we're only going to do 60 frames per second. That means 60 checks. But if every frame, 60 frames per second, if I'm only doing 60 checks, that means that there's going to be a possibility that from one frame to the other, I'm over here. Similarly, if I have 2 particles, let's put this particle over here, and they're dynamic, they're moving. Let's suppose I have another particle over here, and both particles are moving. I might have a case where I'm seeing this before I do a collision detection and response. Or they might pass right through each other. Let's say this, right? We need to reposition them into the place where they would have collided and then make them collide in the opposite directions. We're going to reverse this kind of stuff. Again, this is assuming that the angle of attack is perfectly perpendicular. Otherwise, we're going to go back to what we calculated earlier when it comes to momentum, right? That's right, the time step is going to make them miss. So this is the scenario where we have two dynamic objects that might have an overlap. And we can kind of look at the L value, and the L value is the overlap, right? How much overlap? And we want to move them back along their angle of attack. If they're moving equal speeds, we want to half the L value. If we're moving, one particle is moving faster than the other one, we want to move towards the particle's direction. Okay, and it talks about that here in code. I'm not going to do that here. I'm just talking about it as we move on. All right. And it talks about repositioning, just the same. And that is particles in 1D, two particles colliding in 1D. So there's no energy, kind of being lost on an extra component, as an example. But what happens when particles collide in 2D, as an example? If particles collide in 2D, then we need to do the repositioning twice. Okay, and this goes back similar to that of a ball colliding with a wall at a point of collision. We have to reposition the particles back along that wall. But we can, because they're moving, the great thing is we can assume that the particles are actually bits of wall across the x-axis and the y-axis. We don't have to consider that the particles are particles that are, for example, at an incline. We don't have to consider that at all. We just have to sit and say, well, this particle is actually not at an incline. It's I'm repositioning it from the vertical or the horizontal, and it'll look pretty good. And that's what this talks about here. So again, the steps for 2D particle collisions are the following. Detect the collision, and this is a challenge. All right, sometimes when two particles are dynamic and moving, detecting the collision is a challenge. Number 2 is decomposing the initial velocities in normal and tangential components. So we take the normal and tangential and decompose them. What are they? And then step 3, we reposition the particles at the moment of collision, so when they should have collided. And then we calculate the normal velocities just after collision and apply the new normal velocity components back to the tangential components, which is what we did earlier. And here's an example of some code to do just that, some pseudocode. Over 2 pages. Okay, so I think we've covered a lot today, and a lot of it is what we talked about before. So we covered collision response. We talked about momentum. We talked about impulse. We talked about how particles can collide in a system and how that they'll reflect. Again, a lot of the stuff we can do when it comes to momentum is we can apply some of these same things here. If it's in a 1D system or if it's in a 2D system, and I'm going to find that where the two objects collide. That's still 1D. This one, where you have where there's a 2D collision. All right. There's nothing wrong with using these equations as well to help you, right? We can think about using these equations to calculate the momentum, right? If we use momentum as opposed to trying to use the reversal of those special edge cases, sometimes we'll need to use the momentum, especially when it comes to some kind of angle of attack. As an example, we know the angle of attack. We're going to use the momentum. We're going to decompose the motion into its x and y components. And once we've decomposed the motion, we can apply momentum and kinetic energy to both those components in order for us to get a proper motion in the right direction. And that can help us instead of rotating the coordinate frame, like I talked about earlier. Okay. Rotating the coordinate frame might be easier. It might be a simpler calculation, all right? But we can use this kind of stuff if we need to be more accurate. My challenge is how often an object collides, right? How often we check collisions, right, as an example. That's a problem. And one of the things we have to think about is, do I have to look ahead? We're going to talk about that next week. Do I have to look ahead when it comes to collision detection? Am I always going to have this tunneling effect happen where I check, where I'm checking collisions too late? should I just slow down my particles and make them bigger? Because slowing them down and making them bigger is an easy fix so that the collision detection problem happens less often? Or should I devise another option in order for me to not miss the collision? Because all those steps, notice it says number 1, detect collision. Number 2, reposition. Number 3, right, make the response. What if you can't detect collision? Then number 2 and number 3 don't matter, right? So detecting the collision is part of the important piece that we have to figure out. And what we can start looking at is something called, which we'll talk about next week, something called swept spheres. If I was to look that up for you. If we look at swept sphere collision, right? And if we look at some images, imagine if instead of an object moving along, or think about marching, kind of spheres that are marching across, as opposed to it always going to be the bounding box is this. Imagine if the bounding area is like this, right? A swept sphere or a swept circle, right? Where we extend. Here's the original location of the object, but we're extending it some distance away, right? And then the moment before impact, the frame before, we're going to have a swept sphere collision, not an actual collision. We know that this is going to collide for sure, right? As an example. And what are we going to do? We're going to do a line intersection test to know where the object is going to be colliding. All right, that line AABB check type of thing. Once we know that, then we can reposition the ball, right, to where the particle, we can reposition the particle where along this line it's collided with before it collides, right? We know it's going to collide at some point, but we know also that it might go through, it might tunnel through. So before we do this, we want to kind of skip it back along the trajectory somewhere, along the path. We're going to talk about that next week. Okay? And there's some great, there's also some great, tutorials out there to talk about how to do that, right? So we have one object and another, and you're kind of creating this swept circle or swept AABB type collision detection, because it's going to be too quick. By the time, if we check every time step, it's going to go through to the other side, and what's going to end up happening with that is you're going to have a missed collision. Okay. All right, any questions before we move on for today? Well, we got through the slides, guys. Thank you so much. I know I didn't talk too much about them at the end, but the idea is what I wanted to talk about, right? And some of the pseudocode you have to translate anyway, right? So otherwise, remember next week, guys, next week is when your assignment 3 is due, and we're going to be talking about assignment 4, collision in 3 dimensions. Okay, guys, thank you so much. I will be available on Discord if you want feedback at any time or anything I can do to help you. Please connect with me on Discord, and I'll help you out with your assignment number 3. Thank you so much, guys, and I'll see you next week. Take care. Did you need me to connect with you, Vincent? Yeah, I do. Do you have time this afternoon? If you do, let's see if we can hook up this afternoon around 2 p.m. Okay, thanks. Let me know.